Okay, so we continue on our discussion for chromatography. So, we will discuss a little bit about mass spectrometer for organic analysis. So, the mass spectrometer has the identification of so in a mass spectrometer detector, what happens is this. So, in the regular GC we see that this is a GC column, it goes out and you have the FID or something that comes here. So, the detector is here. In the mass spectrometer is a big detector, it is not a small device like the FID or VCD. What happens in the mass detector is the each peak, everything that comes, anything that comes to into the detector is ionized. So, essentially it is ionized and fragmented, broken into small segments. I am just trivializing the theory of it. Mass spectrometry is a very complex field. It involves the interaction with energy in different forms. In this case, energy is in the form of electrons, high energy electrons, and not that high energy also, it is fairly moderate. There are other devices where you can ionize it to a much larger extent and do further things. But what essentially happens here is that there is a fragmentation that happens of the molecule, the organic molecule that is coming, and each when it fragments, you have the capacity, the instrument has the capacity to measure the intensity of each fragment. Okay. So, for example, if you have a compound that looks like this CECH, so what this can do is it will fragment in terms of CH2, 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 CH3 and so on. So, it knows, and each of this has a mass. There is a certain mass for each of these fragments, and this mass, and there is also a charge because it is already ionized, there is a mass and charge, and based on this mass and this mass by charge, you can separate each fragment. You can analyze for each fragment, just the way we do for chromatography, we analyze each fragment and then measure the amount that is contained in each fragment. So, to give you an example, I will show you an example in a minute. So, what this does is the mass spectrometer has an instrument, has a device called as a mass analyzer. So, the first thing in the mass spectrometer, the first thing is an ionization, is ionization. The sample is coming from the GC, it is flowing, and it ionizes, then there is a mass analyzer, and then there is a detector. This is the actual detector. What we are doing is, if you put the detector here, we are analyzing everything en masse. If you put the detector before the GC, you are analyzing without even separating components. If you are putting after the GC, you are separating components, analyzing it, but you do not have any information about the qualitative part. The detector is here right at the end of it. Before this, you are separating it. So, this mass analyzer, what it does is this the mass analyzer itself is different types of mass analyzers exist, but one of the common mass analyzer is called as a quarter pole. Very simply, it is a channel which is about 4 magnets. If you look at it from the way, these are about 4 magnets that are there, and there is a path. This is the pathway of the analytes that are going here. Let me make a new slide. So, this is a mass analyzer. So, this is coming from the GC, and right here this is the place where this thing happens, the ionization happens. energy is given, large amount of energy is given, and the compound that is coming in, it bombards and it goes, the fragments are going through this. These 4 rods you see are the analyzers. These rods essentially have some, it is like a magnet, very simple terminology, is like a magnet, it's not really, it's some sort of an electromagnetic device. What it does is it pulls, there is a trajectory. You see, some of the things that have a certain mass, what is programmed to do is, it is programmed to allow one mass to go through, the rest of it is pulled out. It is also called as a mass filter. Let us assume that it is like a mass filter, you do not worry about the details of it. What it allows is, there are several M by Z things that are, let us give different colors to it. This is some reds, some green fragments and some blue fragments. These are all going in. What it does is, for a particular setting of the mass filter, it pulls out, if it can pull out all the blues come out, all the reds come out, and only the greens go through to the detector. So, this happens, which means that it is separating the fragments of the component itself. One compound, it is breaking it up into fragments, and one of these fragments is being analyzed, and then it switches to the next one. So, this is from, say, from time T1 to T2, or we will call it as some delta T1, and the next delta T2, the same thing happens, but now it is allowing, it will allow all the green and the red ones are pulled out, it only allows the blue to go through, and so on. And the third time segment, it allows the red ones to go through. Okay. This is done very rapidly, it is done very quickly. So, from time about delta T1 times time interval, delta T2 and delta T3, it is trying to analyze, we are doing M by Z1, M by Z2 and M by Z3 corresponding to 3 different fractions of the thing. Okay. So, the detector is really allowing one of these fragments to go through, and then all this information is then reconstructed. So, the signal now looks like this at one particular time, as the compound is going through the chromatograph GC system and the MS, you will get M by Z1, M by Z2, M by Z3. All these 3 intensities, this is the intensity of the signal, all these 3 intensities together represent the compound that is getting out. So, in other words, in the GC system, as the GC system you are getting peaks that are coming out, right, each peak is coming out at some time. As the peak is coming out, this is a flow system, it is coming out as a function of time. So, each one of these things is going through the detector, this mass analyzer, and at every point, if you are able to quickly scan all the mass by charges. So, if I want to get mass by charges from say 10 to about 200, how do I know this mass by charge? The maximum mass by charge is the molecular weight of the compound, beyond that you can't have anything. So, if the molecule does not fragment, it will come in as it is. So, then the molecular weight will be the mass of that fragment. Okay. So, it does not have anything to fragment, it is all full, and it requires higher energy to fragment, and we are not providing that much energy in the GC. There are some things which are fragmentable in the GC energy. If you need to fragment more, you need to go to really high energies, and you do not have that in the instrument here. So, in the range that you are looking at, while the compound, this is the time that it has. The beginning of a peak to the end of the peak is the speed at which the compound is going. Okay. Within this time, it has to now go and scan everything, all the fragments. It has to scan from 10 to 200 as many times as possible. It keeps going to 110 to 200 as many times as possible. So, it stays for some time. So, what it will do is, it has a certain what is called as a scan rate. So, it will do that. So, you can imagine that if something is flowing at certain speed, So, everything is flowing, right. You have a mixture of these things which is flowing through this mass analyzer. While it goes through this mass analyzer, all of it is going through this mass analyzer, you have to scan through everything. You have to scan all the mass that is of interest to you, and therefore, you will get intensities assuming that this is all well mixed. What we mean by well mixed is that at time at 1 second and say 1.2 seconds, at 1 second and 1.2 seconds the composition is the same, that one of these fragment does not get ahead of the others, which means there will be a problem at that time. So, we assume that they are all well mixed, and then you pull out all of them except one and then measure that. This is the intensity, okay. And this is recreated when the compound comes out like this in the exit. This is the spectrum, this is the mass spectrum of whatever has come out. How do you identify now if this is compound X? You have to check if this is compound X. You have, see all these peaks. So, everything corresponding to this peak has now come out. Okay. So, the intensity of all these three will add up together to the intensity of this peak, that is the general idea. There may be losses, of course, obviously there are losses because this is not the entire thing, you have lost some of them, you are only collecting the signal for a fraction of it, because you are losing all of it here, right? Here and here, you are not analyzing it really, okay. This is another important point to remember. But nevertheless, you get signal corresponding to the fragments of this, and this is, now how do you use this to identify the compound? You have a mass spectrum which is like a signature of this particular compound. What this says is there is a certain fraction of MZ1, there is a certain fraction of MZ2, there is a certain fraction of MZ3. You can reconstruct the structure of the compound using this, but that is a longer method. But is there an easier way of checking if this is a spectrum, this spectrum corresponds to a particular compound? So, this is a signature of this compound. Is there a way in which you can verify, cross check if this mass spectrum belongs to a particular compound A, some compound? How will you verify if this is a spectrum corresponding to one particular compound? Easy method. Huh? Yeah? Time. No, but this is a signature, this is a spectrum. How will you how will you verify this belongs to a particular compound? You have to identify, you have got a lot of data now. This data is a spectrum. So, spectral information is like a signature. How do you know that this signature belongs to a compound?
Wavelength.
Huh?
Wavelength.
By?
Wavelength.
There is no wavelength here. You are talking about different spectrum, we will come to that. We have been doing this all through this discussion. If you do not know what it is, what is one option? Whenever we are stuck like this, we make use of a standard. So, what standard will you check it against? You do not know. So, there is you will compare this there is a library of standard spectra for all known chemicals that have been manufactured and you think it is there in this compound. There is a library of standard mass spectra. Every time somebody manufactures a chemical, they will measure properties, and one of the properties is mass spectra. There are other spectral information that you also get, this infrared, UV visible absorption, a few other things, we will talk about it briefly, fluorescence spectrum and all that. These are information that pertains to the signature of that particular compound. Okay. So, you compare with a reference with all standard spectrum. It is a very painful process, which means compare means I will give you an example. So, suppose I take this peak, this is a chromatogram from a GC and then I take this particular peak, and we have said that now this is a two dimensional thing. So, here this is the time axis and this is the intensity, okay. This is a signal intensity, this is time, and you can see these numbers here 7.5, 10, 12, this is minutes, it is in minutes, this is time in minutes. Now, if I take this one particular peak, I have expanded it in the software, the mass spectrum of this peak corresponds to this. So, the first one here is the mass spectrum corresponding to this peak. So, what I am doing is I am taking the mass spectrum for the entire thing. So, first the entire thing, this peak, the mass spectrum of this corresponds to this. So, you can see that on the x axis here is m by z and the y axis is some intensity again. So, you can see small lines and you can see some numbers, that is a mass by charge, and there is one big number, big peak at 91 and another big peak at 106. Now, I have a library of such spectra. If I do not have a library, I can guess, I can say, okay, if this is benzene, can I go and see if this is benzene really. I know benzene may be in the sample and it is supposed to come around this time from the retention time analysis. I want to confirm this is really benzene. So, I inject benzene and I compare the spectra of reference spectra of benzene. So, this one is a reference standard of benzene, the second peak. So, what it does really is you see that some of the peaks which are there in the first one are not there in the second, and some peaks which are there here probably are not there in the first one. So, we do a match, So, when we do a match, the instrument will allow you this. When you do the match, then you get what is called as a similarity search. In the olden time it used to be done manually, but now software does it very quickly. So, it will give you a match, it says 98% match to benzene, to several things which are all isomers. If you have compounds which have same molecular formula, it will look the same. You have to figure out based on some other thing whether which one of the isomers is this, okay. So, this is for it, because it does not give you 100% again, it only gives you a very high probability of the compound. So, this is xylene in this case, 1,4-dimethyl benzene is 1,2-dimethyl benzene, there is paraxylene, orthoxylene, all these are possible, right. So, that information is not available here, you have to go to some other way of finding out, but that at least you know it is xylene, okay. So, this is the way mass spectral GCMS is used. So, you need, if you have a new compound, you need the spectra for that and you will compare most of the times. So, yesterday's lectures we had talked about quantification, we will look at that a little bit. So, this is how the chromatogram looks, retention time in minutes, detected response. Then I can, current modern softwares, you can do all these things, you can expand and go and look into a peak and all that. So, I am expanding that particular section of the chromatogram, it will look like this, you can see peak shapes, they look very nice thing, but you can also see that sometimes if you notice this point, there is a particular, it is not going back to baseline, it is stopping short, which means that its separation is not exactly nice, but you see by and large there are two peaks. So, it is your judgment whether you can live with that or not. So, there are some statistical tools in which the area calculation is done like this and they will adjust the numbers there, but if the peak is really overlapping, then they will, you have to go back, do a separation again, you have to run the chromatography with different set of conditions. So, this is area under the peak, the number now you are seeing as the peak has been integrated, you see how it has been integrated. They have cut it there and they have integrated the area. So, it is integrated from this point to this point and throughout, yeah. And this is some units, arbitrary area units. So, you can integrate the entire chromatogram, you will get all of these. So, I can get a report like this. So, it also reports for a particular retention time, it will give me the area and the height, okay. Then I can go to each one of these compounds, if I know which one they are, I will do a calibration, and the calibration is done again in terms of say concentration that you are injecting into the GC versus, now we have studied calibration. Calibration can be done in mass or concentration, but here we are doing concentration because you do not know what is happening to the mass in the system. So, your relationship is mainly with the concentration. You are eventually going to calculate concentration anyway in what you are injecting into the GC. So, you might as well do it with that. So, you forget about what is happening inside, so inside the system. So, one of the things that happens in the system, as you have seen, that there is a lot of loss. Loss can happen in the injection system when you are when the compound is getting vaporized, sample is getting vaporized and pushed into the column. It may not come out of the column sometimes, and it may get adsorbed on the injection system. It may get lost in the detector. It may be, for various reasons, compound may not come out fully. So, you do not want to worry about all that. If it is happening systematically and it is happening not as an it is just an error, but it is a regular error, predictable error, you do not worry about what is happening there. If I inject concentration say 1 milligram per liter, I will get some area response, that is all. Every time I do that, if I am getting the same, I do not care how much of one is getting lost in the system, this is happening, that is for sure. Okay. This calibration is done.
If mass is getting lost, then concentration will also change.
No, but that is what calibration is based on that. So, as long as it is consistent, how do you know what is happening in the system? You are not getting mass unit, you are not even measuring mass, you are measuring voltage or something, right. So, that is why we sometimes do concentration calibration, because it does not matter, we do not know how much mass concentration, people do not worry about that. Also, concentration is used directly because volume injected is the same most of the times, it is fixed. If you inject different volumes, then you have a problem. Concentration mass are same, there is no change. The other thing that people do sometimes is, so if the calibration is paramount, so if your calibration is reliable, which means that every time you do a calibration you are getting a linear response, then you are okay with it. So, that is demonstrable, you can demonstrate that, you can you have a good quantitative analysis that you can do. As you can see here, it is fitting a linear curve with 0 with an intercept. Sometimes you can choose without an intercept and all that, that is depending on how your calibration looks, you can do that. You have to be careful. So, the intercept is very large in this case, okay. This slope is 655,238 and intercept is 241,455, which means that when you have, what it means is, physically if you run a blank, what this means is that when you have no compound, it should give you that area, but if it is not giving that area, it means that it is an artifact of the fitting, which means it is really a non-linear fit at that level. So, then it is not reliable really. So, generally what people do is they do not take it all the way to, they will ignore this intercept because they are not going back there. So, they will use this curve in this region, that is all. Intercept is used, it is not ignored, but there is also a problem. Say suppose I can also fit it to 0, it will look like this. If I fit it to 0, this curve will slightly shift a little bit, okay. These issues are there and you have to take a call based on how do you think, how much error is happening and where you are, which part of the calibration curve are you in, okay. If you are on the lower end, then you have a problem, so you have to fix that. Yeah, so we talked about this. Now, sometimes if you have peaks like this, very small peaks, you may get a similarity search that looks, that says 75%. It's your call whether you are okay with 75 or not. You will get a similarity match of 30%, 40%, 80%, 95%, 98%. So, typically from this chromatogram I am not really sure if it is noise or signal, whether it is enough information for me to judge whether it is benzene or not. So, I will discard that, I say I am unable to determine. So, you will say below detection limit some such thing. So, if you cannot identify a compound, you can't even calibrate for it. So, it is equivalent to saying it is below detection limit. So, you cannot detect the compound. So, now one of the things that we have seen is that the goals of the in terms of sensitivity, so we know that the GCMS can be run into two modes of operation. One is called as a scan. Scan is what we just explained. It says that I want to scan the entire range of mass by charges and looking at whatever is there in the system. So, this is what we do. So, normally GCMS is a very useful tool. So, what people get very analysts are very optimistic and they say I want to know what is there in the compound, everything. So, it's potentially it has the power to find out what is there in all organic compounds in the system. I have 100 peaks there, it can tell you what each peak is. Yeah. Problem is, suppose you have a, in order to scan it, this is the mass filter. We also saw that a group of ions mass fragments are going in. We are only analyzing in the detector, we are only analyzing a fraction of what is going in. Okay. So, if you are measuring one fragment, you are measuring it for a certain period of time. Okay. So, let us say there are 10 fragments, each fragments and your total time is say 10 seconds. This detector can only detect one fragment. So, let us say there are 10 into 10, 10 fragments and 10 units of each fragment, right. So, one of the things that happens is if I want to, I have to divide the time that compound goes from here to here, it takes 10 seconds, but I am dividing the time, I am dividing into 10 and I am only giving 1 second per each fragment. So, what happens is I am only able to spend 1/10 of the time for each fragment, and the rest of the time this particular fragment is not going to the detector, it is getting out. The other 9 fragments are getting out except one. So, for the first second fragment fragment number time, for the first 0.1 second fragment 1 is going through, 0.2 seconds fragment 2 is going through and so on. So, it is only one fraction of the time that each fragment is going through, which means that even though there are 10 units of a particular fragment, I am only able to measure one small fraction of it, because at the time it is allowing it to go through. Okay. So, in order to prevent this, what this does is it reduces the sensitivity. Scan which means that my minimum detection limit is high. I need higher concentration to detect it. Okay. So, if there are really large number of units, so the detector has an MDL, right. The detector that we are using has an instrument detection limit below which it cannot measure. So, if I want to get above the detection limit of the instrument, I need to be able to have enough concentration here that goes to the detector. It is the same principle that we are using for MDL in terms of. So, we give the maximum opportunity for one particular fragment to go through the detector. So, when we are doing scan, it is sometimes not possible to do it, even though it is very attractive to do the scan. So, instead if we want to increase sensitivity, what we do is something called as SIM, just called as selected ion monitoring. Selected ion monitoring, we don't look for everything, we only look for specific main fragments. But if you do that, for example, in this case, so let us say that the mass spectrum consists of small things and then 3 big ones. Okay. Now, these 3 big ones are in this mass range here, and there are 10 other small peaks here. Okay. If I want to focus, if I want to spend time on looking at all of them, I am losing valuable time in analyzing these 3, which are significant fractions of it. You will get a very high this thing. So, instead in SIM, what I am doing is I am only analyzing these 3. I will not worry about the others. Okay. So, it gives me more time to analyze the larger mass fractions, this thing. What is the payoff? What is the compensation? So, it increases sensitivity, which means I am able to detect lower concentrations, but what is the side effect? What is the consequence of this?
Long time.
No, time is the same, because what is the difference between this and this?
You don't know what all others are there.
No, what is the difference between A and B?
Not many other compounds.
No, this is one compound, this is a mass spectra of one compound. So, the difference between A and B in terms of information,
Mass reduces.
yeah?
Mass will be reduced. Like
What can you do with this which you cannot do with this? What can you not do with B? If I give you a mass spectrum like this, the original mass spectrum, scan mass spectrum is A.
match may not be
Mass may not be?
perfect.
What is the consequence of that?
The calibration would be different.
Huh?
As in, if your match is not perfect, then your calibration would go.
Calibration is different, but here, right here, we are using mass spectra for something. What are we using mass spectra for?
For many compounds.
Yeah, yeah.
Here we are analyzing only
One, yeah, but here. But what can you not do with this? With this spectra, with A, I can do something. So I cannot do that with B. I just discussed that.
B is not the complete mass spectra of the compound.
Yeah,
It
so
cannot be used as the signature for
you
that.
cannot use as signature. It's unreliable as signature because it's a fraction of the entire thing. It can give you a large signal, but it doesn't contain all these peaks. So when you are doing a match, it will give you a 70%, 60% match. You are really not sure if it's that compound or something else, which means that you have to use SIM. SIM is not used for identification. SIM is used for increasing sensitivity, which means it is used for quantification only, which means by this time you should be absolutely clear that the retention time and the compound that are coming at that particular in your sample is what you think it is. So you have to do a scan to ensure that this is this compound, and then when you want to go to compounds which have, so when you are doing calibration and all that, you are establishing retention time and the identity of a particular compound. So when you want to do quantification, if you want to find out very trace levels, you have to do SIM. So practically what this does is the following. Okay, now you have two problems here. I have an unknown sample which may contain a lot of compounds at very small concentrations. If I do a scan, my chromatogram may look like this. So I will show you. So this is what it looks like. If I take a scan on the top, chromatogram on the top, I have 1 ppm of some mixture. I have a standard mixture, 1 ppm. You can't see anything. It does not mean there is nothing. You can't see anything because it is all below detection limit. But if I change it to SIM, 1 ppm, I can see now peaks. Now what I am doing is I am not looking for everything from in the mass spectrum from mass of 2 to mass of 300 and all that. I am selecting specific compounds and I am looking for them alone, then I get peaks. Yeah. Then I know there are some, then before I get to this point of SIM, I need to know what I am looking for. Okay, which means that I am looking for a specific set of compounds. So which is why analysis of all these compounds, you have to have an objective very clear in the beginning. The objective will be, I am looking for PAHs, I am looking for pesticides, I am looking for polychlorinated biphenyls, I am looking for a specific class of compounds, alkanes. And then you have to set up this program the system to look for only those ions, those mass by charge, M by Z. Okay. So which means that you have to go to the original spectra and pick the mass by charge. So in this case, I have a choice. In this case, say ibuprofen or diclofenac, these are compounds that we want to look in water. So there are some very prominent large peaks. Okay, but I can find out certain which is largest. I can take 161, 163, maybe 91 as signatures, representatives of ibuprofen, and in diclofenac I can take 214, 242, and 296. And I run, and there are a lot of other peaks which it will not detect. It will not. which means I have to make sure using a scan and using my calibration and all that procedure to make sure that the peak that is coming at that time is diclofenac, and the fragmented peak that I am getting in a sample is part of that peak that is coming. So, you can also use this spiking method which I described yesterday in the GCMS. You can take the original compound and do a sim for specific peaks, then you can spike it with the compound of interest. You have a guess now that it could be this, you already know the compound you are looking for, then you spike that compound standard, then you go to the scan and see if it is not showing up, because the scan can detect higher concentrations. Your sample does not have that high concentration. So, you increase concentration and verify whether you are getting the same thing. So, anyway, so this is a very large this thing, and there is other complications in doing organic analysis, especially if you are doing things like organic acids and other things which you need more further processing in order to do this. There is something called derivatization which will increase the stability of the compound during the analysis. So, we will not talk about that here, but the summary of this thing is that full quantitative and qualitative analysis of the system